Hi, welcome back. In this video, we're going to talk about solving absolute value inequalities. In the previous two, we spoke about how do you solve a linear inequality and a quadratic. So we've been focusing on linear and quadratic, all things inequalities, right? Well, we're going to continue to apply some of the same concepts, but with a slightly different function, an absolute value function, and that function looks something like this. Right? Now we're going to review a little bit here in this video in the very beginning to get you recapped on what an absolute value is or what does it do as an operation. And then as the problems progress, I will give you slightly more complex examples until the very end of this video. I'll show you some special cases where we want to be able to pay attention to and an explanation to why those special cases occur. This is a really good time to click like and subscribe if you haven't already. All right, let's do a few examples. Let's review a little bit. What is an absolute value, right? What does that function look like? What does it do? Well, an absolute value is very similar to a quadratic, or it's very similar to a behavior to an exponent of 2. Whenever you take the absolute value of a number, let's say a negative number, the absolute value itself changes whatever is in there into something positive. Yeah? So if I were to plot this as a table, right, at -3, I would get a 3. If I take the absolute value of -2, it will turn into a positive 2. A -1 to a positive 1. The absolute value of 0, well, since it's neither negative or positive, it doesn't change it, it's just 0. And then when you start taking the absolute value of a positive number, since the absolute value changes to a positive, but it's already positive, nothing really happens. Nothing changes to the number, right? So 1 turns into 1. The absolute value of 2 turns or stays 2. Absolute value of 3. And I can go on, right? The idea here is that the absolute value will affect a negative number by turning it into a positive one. And the function looks something like this. This is the parent function of an absolute value function. You might remember this function from previous courses that you've taken in algebra, right? But it behaves very similarly to a quadratic. Right? Parabolas point in the same direction, right? So if I plug a negative inside it, negative times a negative turns also to a positive. Just like the absolute value turns into a positive, right? And there's two sides to the parabola. The left side is symmetrical to the right side. And you can say the same thing with absolute values, right? Whenever I take a negative value and I put it in my function, it'll result as a positive value. Okay? The important thing here is to notice that there's two sides to the graph, or two sides to the function. A positive side and a negative side to the function. And we want to be able to account for both when we're solving these next few examples. We want to account for the fact that the results here, the output, was a result of both a negative or a positive, right? Looking at that alone, we can't really tell by itself whether the value was negative or positive originally. We just know that a negative or a positive can create this outcome. And as long as we can account for the fact that there's two sides to this function, that there are two possibilities, we're going to be able to solve the problems just like that. So let's try some examples. How would you solve the absolute value of less than or equal to 9? Well, I first have to account for the fact that there's two sides to this inequality. I don't really have to know how to graph this inequality first by itself, right? But I know that if the absolute value of a number here is positive, like it was here earlier, right? The absolute value of positive 2 didn't change. It stayed the same. So when the problem is positive inside the absolute value, nothing really changes. So I can just ignore these absolute value lines, right? And just solve the problem as it is. We get You move the 3 over, x's everything are equal to positive 6. Now, because I know that there's two sides to this equation, I'm going to now also focus on the negative. Well, what happens if what's on the inside, if it's a negative value, the absolute value will convert it to positive. So if I remove the lines and I write this problem, I have to account for the fact that there's also a negative possibility, a negative component that results in a positive answer, right? Just like before when we solved a quadratic, right? Whenever we solve these quadratics in previous examples, and we square root both sides of the equation, we get x equals 3. 3 wasn't the only solution, right? The quadratic had two sides, a positive and a negative. So what did we do when we square rooted both sides of the equation? We had to account for the fact that there's a positive and a negative answer. The square root made the quadratic disappear, or the x squared disappear, right? So we needed to account for both aspects. 3 times 3 is 9, and negative 3 times negative 3 is also 9. Well, here, we're going to account for this by removing the absolute value lines. We're going to account for the fact that there's a positive solution and a negative one. So we just solve this as it is, right? We distribute the negative into both, and we solve. Move the 3 to the other side. Negative x is less than or equal to, this is 12. Divide both by a negative 1. X is x is greater than or equal to negative 12. Because when you divide by a negative, this flips over to a positive, so greater than, right? All right, so what are we working with here? If I graph this as an inequality or as a number line, I can graph the solution. So I'm going to go to negative 12, which is on the left. Positive 6 is on the right. Since there's an equal symbol here, we're going to put a closed dot. Same thing here, closed dot. Now, x is everything greater than or equal to negative 12. And x is less than or equal to 6. There's my solution, right? You can write it like this as a number line, or we can even put it in the middle. X is less than or equal to 6, and also it's going to be greater than or equal to, on the other side, negative 12. Now pick a number, right? Any number in this range, like 0. If you plug 0 into the inequality, 0 plus 3, is it less than or equal to 9? Yeah, well, 0 plus 3 is 3. And the absolute value of a positive number does not affect it at all. 3 is actually less than 9. That's why the 0 is part of my solution set. If I plug a number over here, like negative 15, or even over here, positive 10, they will not be part of my solution set, right? I can plug negative 15 into the inequality. Negative 15 plus 3, is that less than or equal to 9? I'm plugging everything into the original one, just to confirm, right? You don't have to do this when you're solving it, but I'm trying to show you why that's the solution set. Negative 15 plus 3 is negative 12. The absolute value of a negative turns it into a positive. Is 12 less than 9? No. That's why this is not part of my solution set. Right? When I plug negative 15, it's not going to be true. Same thing for 10. I can plug in 10. 10 plus 3. We get 13. Is 13 less than 9? No. So we're looking for values between negative 12 and 6 as my solution set. Or we're looking for values greater than or equal to negative 12 and simultaneously less than or equal to 6. Right? The key word that we're going to focus on here is and. Is 0 greater than negative 12? And is it also less than 6? You bet. All right, let's try another one. Here we're dealing with greater than instead of less than. Whenever you're setting up a problem, you want to account for the both aspects of the problem. If I'm going to remove the absolute value lines, and the value inside here is positive, right? If all of this is positive, then nothing really changes. When it's negative, though, I need to account for that part, right? The graph will have two sides, the positive and the negative. So let's solve this as it is, right? We subtract 2 on both sides. 2x is greater than 6. We divide both by 2. X is greater than 3. Now over here, when I distribute the negative, I get negative 2x minus 2 greater than 8. And then if I move the 2 over, negative 2x greater than 10. We can divide both by a negative. Remember, dividing by a negative, switch the sign. It flips it to less than. So let's graph this. What does this look like? Negative 5 is smaller, so I put it on the left. 3 is larger, I put it on the right. Since there's no equal symbol, I have an open circle. X is everything less than negative 5. X is everything greater than 3. Now in this scenario, when we want to describe the solution, we want to use the word or. Because a number can be on the negative, a number can be less than negative 5 and at the same time bigger than 3. It's or. So as you noticed, right, or may have noticed, when we're dealing with less than symbol, or equal to, less than or equal to, we're dealing with the word and. When we're dealing with greater than, we're dealing with or. Something to note to self, right? These two cases deal with or, and these two cases deal with and. All right, let's try some more. Now here, notice how they get slightly more complex in these scenarios. I want to be able to solve for the absolute value part. But before I figure out both sides of the inequality, right, the left and the right side, the positive and the negative, I need to make sure that this is by itself. I got to get rid of the 1. I got to subtract that over, right? The absolute value of 2x minus 3 is less than or equal to 5. Now that this is isolated, we can split it into 2 parts, the positive and the negative solution of it. Because now I want to get rid of the absolute value lines, right? And if I remove them when it's positive, nothing really changes. But if I'm going to remove them when it's negative, I have to account for the negative side of things. Right? This is going to be basically my setup each time. I have a positive where nothing here in the problem, 2x minus 3, nothing changes, less than 5. And then the negative, the thing that changes it, everything here is multiplied by a negative number. Right? That's in essence the process that we're dealing with. And now I can solve this equation and go about the inequality, shading it and graphing it and all of that. Over here, what do I need to get rid of first before I split it into 2 parts? I gotta get rid of that plus and that minus 1, right? I gotta move it over with a plus 1. Now that it's isolated, I can remove the absolute values and account for the negative and account for the positive. Right? I can now split it into 2 pieces. When I remove something from the inequality or from the problem, I need to account for the 2 things that I'm removing from the equation, right? So we got 2x plus 2 is greater than 8. And over here, negative of 2x plus 2 is greater than 8. So the only thing that changes is this. You have to account for the negative of that and the negative of this one. The rest is the same. Just like the previous examples that I've been showing you, we solve the rest, right? Now, if you remember, right, the key thing here that we're dealing with is the absolute value has to be alone before you remove things. I can't remove it at the top because there's a 1 affecting this, right? We've seen this before with quadratics. Whenever you're solving this kind of an equation, right, we said, let's say x squared plus 1 equals 10, as an example. I cannot use the square root method and square root both sides of the equation. I can't just put plus or minus here, right? I have to isolate the variable first. I got to get rid of this piece. Once it's x squared equals 9 and there's nothing around the function, now I can square root things and get rid of it. And since I'm getting rid of something, I have to account for the two possibilities, the two solutions, the positive and the negative. Same thing here. You have to make sure that you first isolate this part. Can you isolate that component, move everything to the other side before you split it into two pieces, before you start to change the problem to plus or minus, right? I got to do that here too, 2x plus 2. Move everything else to the other side. And when you do, you can now get rid of the lines, or you can get rid of the absolute value and account for the plus or the minus, just like we did here. We got rid of the square by square rooting it, and we accounted for it. Same thing, right? So if you feel comfortable with this, move along a little bit or see me solve it, right? We're just going to do more of the same. 2x is greater than 6, divide both by 2, x is greater than 3. I'm assuming that by now you've already done or have practiced on linear inequalities. If you don't feel comfortable, I recommend going back to 2 videos, right? Solving linear inequalities so that you're comfortable doing these on your own, right? Distribute the negative 2x minus 2, move the 2 over, divide both by a negative 2. The sign is going to flip here every single time because we're dividing by a negative, right? And I can graph these. X is less than or negative 5. X is greater than 3. 3 is over here, right? X can be less than negative 5, or X can be greater than 3. Only one of those things has to be true. The solution can be here or here. It can be in both, right? This can't be an and scenario because it can be a negative number and greater than 3 at the same time. Or over here, we're going to move the 3 over. 2x is less than 8. Divide by 2. X is less than or equal to 4. Over here, when you distribute, you'll get negative 2x plus 3. Move things to the other side. Negative 2x is less than or equal to positive 2. Divide both by a negative. The sign flips, right? This turns into negative 1. So when I graph these, I got x is less than or equal to 4. It includes 4, and it also includes negative 1. Here it's greater than negative 1, and, keyword, less than 4. Right? If I plug in a number here like 0, 0 is greater than negative 1, and at the same time it's less than 4. And is a key word here. All right, guys. Now, what I do want to talk about is special cases. Let's talk about some special cases that come up. The setup is the same. We're going to solve these the same, but something comes up along the way. Let me show you. And I'll also explain to you why this happens, right? I'm going to count the same for both sides of the equation. If this part is positive, x plus 3 stays the same. If it's negative, we account for that. X plus 3 is now a negative value. And we solve them the same. But look what happens. When I solve this over, x is less than or equal to negative 8. Now, because it's less than, what am I picturing here? I'm picturing and. Right? That's a key word I want to use. If it's greater than, I'm picturing or. Now, remember that and is when you're graphing between 2 points, right? And or was when we were dealing with 2 different sides. Like, that's where I'm visualizing where things are going, right? So, as I solve for this, negative x minus 3 less than or equal to negative 5. Let's solve for this and see what happens. negative x is less than or equal to negative 2. When I divide, it flips over. Let's graph this out. Check this out. X is less than or equal to negative 8. So negative 8 is on the left because it's smaller. Less than means to the left. Greater than 2. It goes to the right. Remember, the key word here was and. Can a number be less than negative 8 and be greater than 2? Nope. Right. We have an error here. This is a special case. Since a number cannot exist on the left and on the right at the same time, we have no real solution. I'll explain why that happens in a little bit. But the key word here is I was expecting it to be shaded between the two numbers that I found. And I ended up shading away from it. And that's not possible, right? I can plug a number in here in this range that's also in that range at the same time. Now what happens here when it's greater than? Something similar happens. I'm going to account for the positive side where nothing changes with the x minus 2. And then the negative side, I add a negative to the same problem. Right? Move the 2 over. X is greater than or equal to negative 2. Over here, when I distribute negative x plus 2, solve. Negative x is greater than or equal to negative 6. Divide both by a negative. X is less than or equal to positive 6. So let's graph this. What does this look like? Remember, here the word is or. That's the key word that I'm focusing on. The answer could be less than 6. So let's go to 6. Now I'm going to graph this in 2 separate colors. Yeah? And then negative 2 is also part of my solution here. Negative 2. Let's do this in red and in orange or something else. If x is less than or equal to 6, it means that it's going to be everything to the left. Yeah, everything that way. If x is greater than negative 2, it's going to be everything to the right. The key word here is or. It doesn't have to be both things, right? It just has to be one or the other. So when I look at this problem, if it could be the red one or the orange one, then what's a possible solution? Everything's a possible solution. Because any number here, here, or here will satisfy this condition. Try it out. Plug in negative 10. Plug in, say, 0 and plug in positive 10. When you plug in negative 10, negative 10 minus 2, right, turns into negative 12. The negative 12 turns into positive 12. Is that bigger than negative 4? Yes. This is in my solution set. When you plug in 0, 0 minus 2 is negative 2. But that negative 2 turns to positive 2. Is that still bigger than negative 4? Yeah. That's part of my solution set. If I plug in 10, this is a 4. 10 minus 2 is 8. Is 8 greater than or equal to negative 4? Yes. On all 3 cases, they all work. And if we shade the entire number line, what is my solution? All real numbers. Here, we got all real solutions. We were expecting shading to the right, shading to the left, but it doesn't look like that, right? Since I shaded the whole line, it's all real numbers as my special case for greater than. And for less than, because it contradicted what we were expecting, we got no real solutions because the answer couldn't be negative and positive at the same time. right? Now, why do these happen? Well, these happen because when I split the problem into two parts, right here, when I started to split it into two sections, notice how the answer was negative. Could I ever take the absolute value of anything and get a negative result? No, because the absolute value of anything, positive or negative, always gives you something positive. Because it gave me a negative, I knew it was going to be a special case. It was going to create something weird, right? Same thing over here. When I split it into two parts, this one was equal to -4, and this one was equal to -4. The absolute value, right? Plug in -100, it turns into +4. Plug in +100, it stays +4. Like, we're never going to get a negative scenario. So whenever the inequality equals something negative, I'm going to get either one of these special cases. It's going to either be a no solution or all real numbers. Yeah? So how do I know that when this happens? If I have these scenarios, how do I know if these are going to be my special cases or not? From just looking at the problem, I cannot tell. I have to solve at least one or two steps. So let's solve this a little bit. Let's move the 4 over. X plus 2 less than or equal to -3. When I split it into two parts, see how we have a negative? The absolute value cannot be negative. It didn't start negative, so it looked like a regular problem, but it turned into a negative. And the absolute value cannot result as a negative solution. You solve the problem the same way, and when you graph it, I'm expecting and here. So when you shade the problem, I'm expecting something in the middle. But as you solve this problem, you'll see that instead you're going to end up getting something in opposite directions. And a number cannot go to the left on the negatives and be on the right with the positives at the same time. The and part makes it a no real solution. Is this a special case? Well, let's solve it a little bit. Move the 4 over. Yeah, I have another negative. But now it's going to be a greater than scenario, right? So because at this step is where I can identify if it's a special case. Not in the beginning. In the beginning, look at all of these were positives. Everything was positive. But when I isolate this and I remove the absolute value, when I remove it from the equation or the inequality and it equals a negative, that's when I know it's going to be a special case. And as you solve the problem will tell you what type of special case. Is it a no real solution or is it an all real solution, all real numbers? It's going to be one or the two for my special cases. Right? I can tell you that the less than will have no solutions and the greater than will be all real numbers. But I don't want you to memorize this. I want you to be able to reason through it as you solve the problem. Let the graph remind you that and cannot exist on the left and on the right at the same time. A number can be this or that. Yeah. Here, is this a special case? I have negatives. Is it a special case? Let's find out. Move the 7 over. Here, when I split it into two parts, am I splitting it and does it equal a negative number? No. This is a regular problem. There's no negative like there was here or here that created my special cases. When I split the problem, it's positive, and that's not a problem at all. It's just a regular problem. Yeah? So you cannot base the special case in the beginning. The special case happens when you remove the absolute value. Here, does it equal a negative or a positive? If it's positive, regular problem. If it's negative, though, we have an issue. All right, guys. That's my bell. That's my cue. I hope this has helped. Please let me know if you have any questions. I'm going to put here, not a special case. Just solve. For all of them, just solve. You'll identify when it's and or if it's a special case or not. Let the math guide you there. Yeah? You guys have a great day. Don't forget to like and subscribe. And as always, I'll calculate.